I will tell something about use of remote sensing in flood forecasting systems. Maybe I can. And operational water management. And I will tell something about what we do at Deltares and how remote sensing is being used in projects that we are doing for water managers worldwide. Yeah, much of our focus is focusing on this early warning and reducing residual risks. And that is, of course, that early warning systems are the best way to reduce risk of loss of life and economic losses. And this is already known for quite some time, and that's why we develop tools, software that can help organizations worldwide that focus on this. Flood forecasting is focused around. Is focused around integration of data and models. So we developed a tool called Deltares. I will tell more about it. That basically organized this process of gathering all the data you need, and then also, if needed, you can run your model, either LUN models, spatially distributed models, river routing modules, hydrodynamic models, water quality models, etc. Depends on the problem that you have an interest in. So that is the Deltares system that is used quite a lot worldwide, and developments, the early ideas about this way of working. So I'm not focusing on models or only data. We made the data central in our thinking, and so it's a management of the data, and a model is something that can help, but it's not the central team in this process. And here you see a map with all different kind of applications, sometimes pilot applications, but a lot of these systems are operational and produce forecasts day in, day out, covering a vast amount of areas and people around the world. Show some example system graphs. You see the Netherlands on the top left side system that is used to forecast the river flows of the Rhine and the Meuse into the Netherlands, but also the Bureau of Meteorology is using a view system to basically forecast floods in the whole of Australia at a day in, day out. The same holds true for the Environment Agency, SEPA in Scotland and Wales as well. And also the National Weather Service in the US is using this view system for management of their data in an operational setting. We are not only active in these kind of countries, but we also have like systems in other places like Vietnam, Thailand, Indonesia, etc. And not only focus on flood forecasting, but there are also a lot of hydropower companies that are using this software for management of their reservoirs. But because the focus is on flood forecasting, I won't talk about that too much. The system can easily integrate external simulation models. As already said, distributed rainfall runoff models, water quality, 2D, 3D flood models, reservoir models, storm surge if you're interested in coastal flooding, but also sewer systems if that's of interest. And then you can use this model to simulate the future. This is an animation of a distributed hydrological model that produces forecasts for a specific point that you can then either display in a spatial display or in a time series display. You can run ensembles very easily within the system and then produce relevant information for warning of civil defense or other people. The system is highly configurable. You can develop your own informative displays, spatially, but also time series displays. You can use SVG kind of figures, and then you basically the numbers show up in the in these displays, and you can have like very fancy time series displays. So recap, Delfuse is a data and model integration platform. It's not a model, it's a data-centric forecasting system. It's only used to organize the data process from input to forecast to dissemination. It has an open approach to integrate models, any model. It's system independent and very scalable. You can fully configure it. If you, of course, there's a learning curve, but it's definitely doable. And the software is free of charge with a central role for the user community, which is quite large, as you can imagine from one of the earlier slides of all these systems. And Deltares is not the only organization that helps implementing these kind of systems, but we work with a lot of other organizations that either together or on their own can implement these systems for certain regions. And there's a very big user community. So we organize yearly international Delft user meetings in Delft. That's always somewhere in the end of October, November. We also have a national, so a Dutch, more focus on Dutch users. That's in June. And we also organize occasionally local Delfuse user days. For instance, this is in Latin America, but we also have these kind of things in the US or in Australia or in Asia. And last year we also had one in Africa, where we basically provide an overview of what the status is of the software, what things have been developed and changed, what projects are busy. Then we also invite a lot of users to tell about their experience and what they develop and what they do. So that's a big, relatively big community worldwide, very specific. It's a niche community, but it's a very broad community. So now I will switch slowly to use of remote sensing in these kind of systems. So I made a slide that basically recaps how basically it is used. Forcing of models, that's a typical use of remote sensing products for flood forecasting. Rainfall radiation, I will show examples later on. We also use the data to initialize our models. Think about reservoir, you could do it with soil moisture, snow, or flood inundation. We use a lot of remote sensing data at Deltares for developing models. We use the digital elevation model, land use maps, but also LAI observations. And basically derive irrigated areas based on land surface temperature data, for instance. But we can also use it for validation of our models, so flood inundation. And the other use, I will show some examples, is not we just produce images, for instance, of reservoir storage or translate to volume, or river ice, and flood inundation. So these are typical examples. I will show some examples in the coming couple of slides. So this is an example of the Dutch system, where we basically use downward shortwave surface radiation data to calculate potential evaporation. This has been implemented already a couple of years, and is being used now day to day in the flood forecasting system. And in the old days, we used static climatic estimates, but now we use dynamic data to drive our distributed models. Of course, rainfall, as I already mentioned, is used quite a lot in systems, especially in places where rainfall is not measured through gauges or in other ways, like radar. For instance, in Africa, we use, for instance, SuseNet. This was already used, I think, in the very early days already, where we developed example systems or systems in the 1990s. So this is quite a common use. Another example is because the access to data has improved quite a bit. We use, for instance, this is an example of land surface temperature data that is being imported through an OpenDAP server directly into the system and can be used for analysis. So the access, once it's easy and it follows standards, it's quite easily to import it into the system and use it for any purpose. This is an example of use of rainfall data in the Fuse Mekong system developed for the Sphere project, where we basically import this rainfall data and then use it to drive hydrological models. Yeah, this is quite a typical use of remote sensing data. And of course, the advantage of this rainfall data, it's relatively it's available in near real time, in contrast to some other products, remote sensing products. Then I come to a completely different example, where we basically did for the Australian Climate Service, where we set up distributed hydrological models, WFlow SBM, and Sphinx models, which is that's a model to calculate 2D inundation, super fast inundation solver for coastal flooding. I think that's where Sphinx is derived from. As you can see in the figure, you see Sphinx 1, 2, 3, 4, 5. So we have set up 13 models, 13 Sphinx models, but also 13 WFlow SBM models, covering New South Wales, Queensland, and Northern Territory. And for these setting up these models, we of course use remote sensing data like the digital elevation model, but also land use and LAI. And then we can use remote sensing for validation data. And the idea behind the system is to basically, this is an example for a specific location. We get observed and forecasted precipitation. We want to know the water level in the river. To calculate that, we need an upstream, because we don't want to calculate the whole catchment, because maybe in the mountains it won't flood. So we have a distributed hydrological model that calculates the upper boundary of our Sphinx model. That's what you can see in the graph. And then we get a boundary condition from the coastal side from a hydrodynamic model and forecast. And then using the Sphinx model, we can basically calculate the water depths, the maximal depths, and derive a shapefile. And the shapefile can then be used directly by the civil defense or the blue light services, etc., in a certain web environment. And of course, you can then compare these shapefiles that are derived from these models based on the input data, compare directly with remote sensing data. And this is an example. These are two examples how well it compares. Of course, it depends a lot on the input data, but also on the digital elevation model that is available, how good the model is performing. But this is just an example. From this tropical area with a lot of problems, especially during hurricanes passing by, we moved to Canada, where they also suffer from flooding. And this flooding is often caused by ice dams. When these ice dams occur, you get all sorts of issues, and you can have flooding caused by these ice dams, causing a lot of problems. But one good thing is that you can monitor these kind of things pretty well from space, because when the ice is breaking, the properties change, the reflection is changing, and that is something you can monitor quite well from space as well, especially for these larger rivers in Canada. So we started with a project to basically do everything in the Fuse system. Not everything. We did some pre-process, download the data, cut out all the tiles along the rivers, otherwise it would be too much data to ingest in the system. Then make it viewable within the system, within the Fuse system, for the end user. This was done in co-creation with the end user. So we developed this for them and then discussed this with them. And then and also came up with the path forward, how to proceed. So this is an example of the raw image, but also the image in the Sentinel hub, and also then how it looks like in the Fuse system. So that is relatively well. Yeah, you can easily include it in the Fuse system as an image. However, yeah, because we want to, normally you have clients that have this system, they have to do everything, but because the idea was that many organizations in Canada wanted to use this data, we came up with a different setup. Basically, when we went from doing stuff in Fuse from on-premises to the cloud, and then provide the data as a service, basically as a web mapping service that you can then overlay in the Fuse system quite easily. And that is now like a data service we have set up and provided this year to all the Canadian end users. So that's, I think, 7 or 8 provinces that use this data, but also other organizations. So this is then basically the setup we are using. We downloaded the data from these databases. We do the processing. We derive the products. We put it in a bucket and connect to a WMS server, and then the WMS server and client this can then easily directly be shown in the Fuse system, overlaying other maps. Now, something completely different is then, this is then again back to the Mekong. This is flood inundation modeling, or at least monitoring. We developed for this Sphere Mekong project, Arjen Haag, my colleague did that. Where you basically can see the flood developing based on the satellite data. And in the bottom figure or movie, you can see a pilot study we did for the World Food Program, where we basically overlay these flood images with roadmaps to derive basically the risk of which roads are accessible, which were not accessible for the World Food Program to organize their the relief efforts, so to speak. I think that this was quite a successful project with the World Food Program, although I don't know what the status is at the moment. Then coming to the end, we basically also have developed the Global Water Watch, where we basically monitor globally reservoirs around the world. As you can see, you can then zoom in. This is a publicly available website. You can download the data also. And then it looks a little bit like this. As time series, you can download it as time series, but it's based on analyzing images of surface water area, as you can see in this animation. But this data is then also being used to basically initial. Now we are in the transition to go from area to volume. We have developed some scripts for doing that, and we are in the process of using this data to adjust model initial states of reservoirs, for instance, in a project in Egypt. So overall, the use of remote sensing in flood forecasting is increasing, especially with the better access and availability and increasing resolution and accuracy. And of course, also in places where there's no other data available, it's often one of the sources that we always incorporate in our models. And as shown, you can use it as forcing, and that's apparently the rainfall and the radiation data. For model building, often done offline. The model validation, for instance, the flood mapping. State updating, adjusting this reservoir area volume. Then we import the data in Fuse and then adjust the reservoir volume of the model and then run the model. And yeah, we can also develop product services such as the river ice web mapping service that is available in Canada. That is hosted in, I think it's on AWS cloud service. So there are some costs related to that, but that's rather limited for the users. And then this reservoir service areas, now we try to translate it to volumes. That is also a developed service that is now available. We work a lot on this flood inundation mapping kind of things. My colleague Arjen Haag is doing that. I didn't talk about erosion. Coastal erosion is also something some of my colleagues are working on, which is also related to flooding, of course, but it's not really my topic, so I left it out. And the water quality I didn't show, but it's of course, all the things we can do for flood inundation and stuff. You can also look at water quality, several things like the color of the water, etc., and changes. Monitor all sorts of things related to algae blooms and that sort of thing. And then, of course, one of the things we also try is to translate it to impact, as the example of the work we did for the World Food Program. But in the end, all these efforts are aimed to basically develop, basically on the ground and real data or services that are being used by DelFuse users or water managers and beyond. And then, of course, we want to improve our modeling offline and forecasting and the handling of floods and impacts, flood impacts. To contribute to a world safe from flooding. That is also one of the missions of Deltares, so to speak. So this is my end of my presentation. So if you have questions, then let me know. I think I'm pretty well in time. So
yes, thank you. Thank you very much for your very rich and very interesting presentation.
So I didn't speak too much about the remote sensing and details and stuff, but I thought maybe it's more interesting to learn about how people are using it in practice.
Yeah, you gave many examples of that. Thank you for doing that. Before I will give the floor to our participants, so please, please share the questions in the chat, or you can also raise your hand. Maybe I will start with a question. Since when has the system been operational, and how you can access the system, or is it, sorry if I missed this information, but how the user can access it?
We started developing the DelFuse system in 1992. And then it was first proper release of the software was in around 2003 when the Environment Agency started to use it. And since then, we have developed on and off. There are 2 releases of the software per year. You can download it from the Deltares website. I think it's open source software.deltares.nl. It's free of charge. You can download a copy of the system, a copy of the software there, and then use it to start playing around with it. So that's the DelFuse software itself that is readily available. As I showed for instance, the Global Water Watch, it is just a website you can go to directly that was developed a couple of years ago. We are still looking for projects to develop it further. Last 2 years ago, we had a small project of ESA to extend it to from area to volume, so to speak. So we developed some scripts for doing that. So we are looking to improve these kind of services. And for instance, the river ice system was, I think, started developing with some funding from ESA. And then in the end, we are now doing some small projects for Canadian users to basically really go from pilot to a data service that is a project we do for Canadian end users. And then they already are using a Fuse system for the flood forecasting and the water management, so they can easily incorporate the WMS layer into their system.
Okay, great. Thank you very much. I see one hand raised. So Jorge, please go ahead.
Yeah, I have one question, because you were presenting different use cases and different areas where this was implemented, and probably each one has its own difficulties. So I was wondering, what is more or less a common source of difficulties that you have found? And in terms of data sources, which is the data source that represents better or captures more of the variance of the end result? I'm curious about that.
Yeah, it depends. Thanks for your question. That's a good question. Depends a little bit where we do projects, of course. So if we do projects in US, Australia, Europe, whatever, there's a relatively good highly educated people. There's a lot of capacity basically around to take it up and take it over and develop it. But if you go to other places like Africa, but also smaller in SIDS or whatever, it's always problematic if you come with this. Basically, you have like a jaguar of capabilities, and then it's difficult for these people to drive such a fancy car, so to speak. Or you educate people in such a project how to use it and how to develop it, and how to use it in operations. But often, once they are educated, they move on to a higher paid job, so to speak. So it's difficult to keep basically people that you have educated as part of the operations. That's what. So the maintenance part in, say, poorer countries, that's difficult to organize, and but also that's also from the funding side. I think people always interested. Oh, let's develop a flood forecasting system for this country or this catchment or this whatever, and then they forget that after the setting it up and stuff, everybody's enthusiastic. But of course, the hard part is in the maintenance and basically the yearly maintenance, support the maintenance. If there are questions, how can they reach out? Do they have some funding? There's not a lot of money that is needed for that, but that's often forgotten. Related to the data, if you look in the operational flood forecasting area, so this is not related to wherever you are, but it's always the most difficult part is organizing the data flow. So gathering all the data, all sources, all the data streams, and if something goes wrong in the forecasting process, it's often it's not so much in the models or whatever, but it's often that the data stream is not available or whatever. So often you see that although most scientists are much more on the modeling and comparison models with satellite observations, the operational difficulties often in the data streams and making those kind of as stable as possible. Luckily, I must say, some of these, and in the early days with remote sensing data, it was often very difficult to get the data or find the data, and then they were also moved around. So 1 year here and then next year on that another website, etc., etc. So, for instance, this EUMETSAT data through the lens service of Copernicus that is now available through an opened up server, that makes it much easier to start using this kind of data in operations in a very stable manner, so to speak. So, and then even that's possible then also in places like Africa, which is very good.
Thank you. Thanks.
Thank you very much. Another question from Nancy, please go ahead.
Yeah, thank you. Hi, Albrecht. My name is Nancy Searby. I manage Severe at the headquarters level of NASA. And so thank you for your work working in the 2 different regions with severe. I think I have a big picture question and a more practical question. The big picture question is, I'm sitting here now, I just opened the 30 countries that were announced in August of 23 that should have the initial focus for early warning for all, and then of course the challenge from the UN Secretary General was all countries should have early warning by 2027, which is very, 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 very soon, right?
Yeah.
And then if I'm selfish and just talk about where severe works, for example, I look at Latin American, Caribbean, Guyana, Haiti, Barbados, Antigua, Barbuda, Guatemala, Ecuador, right? And in fact, next month, many of us will be in Quito, Ecuador for AmeriGeo Week. And in fact, that whole meeting is hosted by their disaster resilience group. And they're having a first day just to collaborate across their own country before we go for the more international perspective. So I'm mentioning all these little bits of network, right? Human network that are, I think, also important in this whole thing. And then my question to you is, like, you all are known for your expertise, right? Which is great. But as we all know, there are different models. Science is always changing. The constraints of ground-based data to validate is always there. Yeah. So, like, given your expertise, I'm asking you quite earnestly how, if you were in charge for the day, or the next 18 months, actually, because that'll be 2027, like, how would we as a scientific community, frankly, that care a lot, what would be the best strategy in the next 18 months to make the most impact on the people on the ground who need these early warning systems, right? Given the fact that you've got the European systems, the NASA systems, the Deltares systems, ideally you'd have country-led systems, but as you said, it's not always there for many of these countries that we're working with. Sometimes it's because we don't give it to them or work with them well. Sometimes it's because they don't have the people there to do it. Sometimes they don't have the internet or the compute, frankly, right? So anyway, you're in charge for the next 18 months. Given all the work, and you mentioned the WRI system, right, that you all worked on, and that it's got surface area and only volume. My second question is about whether you're going to use SWOT data or you're using radar data. But my first question is more big picture, like, advise us with your expertise in the next 18 months. If you could get all the space agencies to actually work together, if you could get all the aid agencies, the other donor assistants, to work together, what would you do?
Yeah, good question. It's difficult to answer, I would say, because I see this. Yeah, I see the same issues as you more or less point out. You have all these different how do you say it? Yeah, basically what you see often, you do a project somewhere in, for instance, say Africa or another country. You are working there, and the project is funded by this organization, and then once the project is finished, then people don't have the funding anymore. So then the next person with his own funding from another organization is coming with different tools, etc. So ideally, you organize this a little bit. Sometimes not for countries that have the capability and capacity to basically do it themselves completely. Of course, then basically national or catchment systems would be preferable. That requires of course, a lot of communication and effort. Also, for instance, we have implemented a system for the Balkan region together with all the countries there. Fuse Sava was it called, covering 5-6 countries, and then everybody was using the same system. So it's often these operational systems, and also the early warning part is a lot about the communication and having a common understanding. So ideally you organize it also with the Caribbean, for instance, in mind. You see a lot of initiatives, but the overarching part, so arrange the capacity building part, the systems building part, you could organize it at a slightly higher level instead of doing it country by country, but try to sit down with some organization that can support some of the modeling, the flood forecasting, the data management software, as I described, some of the modeling that is being done, etc. And then organize also the capacity building at a somewhat higher level, I would say, than country by country or city by city. So that depends a little bit where you are in the world, how to do that. But I think for the Caribbean, that would probably be a very good thing to do. But yeah, still I see there also efforts that it's not being done. And yeah, you see things that are arranged at that level, but other things are not arranged at that level. So ideally, yeah, you have to have and then involve the players that can do this kind of work, and then keep not only implement a system only once, but also arrange the support and maintenance part. Because I think, yeah, it's nice to say in 2027 everybody's covered by early warning, but what happens in 2028 and 2029? So I think that is the big issue, I would say. So I don't really have a good answer for you, but I would organize for some areas in the world. I would organize at a slightly higher level. Make sure that you involve relevant players that can also support later on the support and maintenance part in a proper manner. And then it doesn't mean that, of course, everybody's looking for projects to do or funding, etc. So also consultants, local consultants, but also more other consultants. So those should also be involved in such a setting that everybody has a role. But that's a lot of organization that needs to be done.
Yeah, right. Thank you. And we have Jorge from UNUSA, but of course, UN itself is a large organization. And
yes.
So WMO. And so like finding that right place to do that kind of organization, I think is part of the challenge.
It should not be too high, not on a too high level. It should be relatively pragmatic, but that you have people that understand the issues also on the ground. So
yeah, I would just say that in our own world of United States, one of my programs called Develop does 10-week projects, and we work with Fairfax County, which is the county I sit in Virginia, and at the county level, not even the city level, but for us, that's the county level, pretty big county for Virginia. There were challenges with trying to do flood prediction because actually at that scale, it's not so great, right? And now you get into urban flooding and it's a research area. It's not even an operational system. And so there's lots to do, but in fact, that's where the impact is managed, right? I get my little aerial warnings of floods on my phone from NOAA, but it's downscaled to my, at least, region. I don't know how they don't give me the geography, which I wish they did, but I'm a geek, right? So anyway, okay, last question. The use of surface water ocean topography data, obviously that's now coming online. Obviously a value to the work you did with WRI, for example. So are there plans to start?
Yeah, we are looking at the SWOT data definitely to develop either what sort of monitoring, whatever, included in our processing. So these tests are ongoing, I cannot say. And also radar, I just received a paper of a colleague of mine who's using the radar data to basically derive water level data over whole river stretches and stuff. So definitely we are looking at those kind of new missions and data sources. Yes.
Yeah, great. Thank you. And thanks again for all your work and your thoughts and your wisdom. And it's complicated. I agree. But I appreciate that you keep working in, and you've been working in all the different regions. I mean, Jorge will bring up the EOTA and the case of like the hurricane with the flood clouds, and the models were all wrong, right? And so like, how do you get to a better solution and be trusted is also the challenge, right?
Cool.
Thank you.